Welcome to bonding. This is going to introduce the general concepts of bonding. So what is a bond? It's a force that holds atoms together. So what type of bonds can we have? We can have ionic, where electrons are transferred. Which is typically metal and nonmetal. Polar covalent. Two different nonmetals. And nonpolar covalent, which sometimes is just called covalent when they're shared equally. That's when you have two of the same non-metal. Sometimes when we have two different ones. So we're going to look at the different types of bonds. We are going to look at bond energy, the energy required to break a bond or released when a bond is made, and bond length. So what determines what type of bond do we have beyond just whether it's metals or nonmetals? And for that we have to look at electronegativity, which is the ability of an atom to attract shared electrons. Remember on the periodic table, it increased going this way and decreased going this way. So we have sort of a spectrum. We have nonpolar, polar, and ionic. Sharing equally to transferring, and it's a continuum in between. So a polar covalent molecule is in between. It has some ionic and some covalent character. And the greater the electronegativity difference, the more ionic the bond. In general, we look at an electronegativity difference. So difference, remember, means subtract. Now if we have the molecule H2O, we just need to look at the electronegativity difference just of the bond. It doesn't matter that there's two hydrogens in it. So the values, we find them on a chart. Oxygen is 3.5, hydrogen is 2.1, so we have a difference of 1.4. So water would fall in that polar covalent range. If we have a difference of 0.4, we're going to consider it nonpolar. It's not perfectly equal, but it's close enough. Now up here at this upper edge, the 1.9, you've got to use some judgment. If a metal and a non-metal, I know I wrote no metal, then it is ionic, even if the difference comes out to be 1.7. Now we know that in an ionic compound, like NaCl, we have Na plus ions and Cl minus ions. Well, in a polar molecule, we don't have separation of charge, but we have this part of the molecule is more polar, more negative. This part of the molecule is less negative. So we could draw it like that. So there's more electrons over there. We could show a plus sign with an arrow pointing to the one that's more negative. And This happens for a diatomic molecule like the HCl that I just did, and for the H2O that we were just talking about. Well, the hydrogens are both partially positive, and the oxygen partially negative. That is a lowercase Greek delta. So the dipole moment would be that the center of positive charge is this end where the hydrogens are, and the negative is the oxygen. Now we can have molecules that have polar bonds but do not have a dipole moment because their bond polarities cancel each other out. It happens with symmetric molecules, so we're going to need to be able to draw structures, which we're going to get to later in these notes. But if we have something like this, this bond is polar, this bond is polar, but those dipole moments of the individual bonds cancel each other out, and we have no dipole moment.